I'll hand over to our next speaker, who is Ben Robertson. He's speaking on reducing operational toil when responding to your next critical CVE. Thank you, Ben. Big round of applause for Ben.
Hello everyone. I'm here to speak to you about how to reduce operational toil when responding to your next critical CVE. First, before we get started, I'll just touch on briefly what a CVE is. So CVE stands for Common Vulnerabilities and Exposure, and it's run by the MITRE Corporation. And CVEs are assigned a number by CVE numbering authority. So when a vendor has a vulnerability, they will apply to a CVE numbering authority to get a CVE number, which consists of CVE plus a year that it was released plus some arbitrary digits at the end. And CVEs come out with a severity rating, 0 being the lowest, which I don't think any of them have, and 10 being the highest. These are made up of a combination of how easy it is to exploit the vulnerability, whether it's remote or local, unauthenticated or authenticated, and what the impact of it is. So who am I? I'm Ben. I work at Puppet as a professional services engineer, advising customers on DevOps practices in a post-sales role. Many of the customer engagements focus on OS hardening and process automation. Previously, I've worked in commercial and government gateways and had a lot of exposure to blue team activities, so OS hardening, perimeter defense, setting up logging aggregation, IPS, and things like that, and also fixing CVEs when they come out. So I'm just going to touch on a few older vulnerabilities, a slightly newer one, and then talk about how we can reduce operational toil while trying to solve one of these as an example. So here's some vulnerabilities from the past: shell shock, heartbleed, and log4shell. Shell shock and heartbleed were both from 2014. These were quite big. They both made mainstream news, like ABC News, New York Times. And if you're working in IT operations or security, you would remember these vulnerabilities from these days. And log4shell was 2021, so much more recently. So just, that'll be close. So just to briefly touch on shell shocked. That was a vulnerability introduced into Bash in 1989, so it had existed for about 25 years before it was discovered. Consisted of 6 CVEs in total. The initial was rated 10. The reason for the 5 additional CVEs is once security researchers started looking into the vulnerability in Bash, they found a lot more similar vulnerabilities. And why was this a problem? This primarily affected web servers that were using CGI Bash handler programs. So the web server would take the input from a user and pass it through to a Bash program. The problem was when it saved that variable as an environment variable, if you formatted your input as such with the brackets and more brackets and semicolons, Bash would actually execute the command that was run after it. It was actively exploited in the wild. Cloudflare offered free protection for their customers and published some useful stats on the attacks. They were seeing around 10 to 15 attacks per second at one stage, and that was legitimately one of the attacks they were seeing, that users were trying to eject CD drives from servers, which was quite funny. But most of the attacks were used for information gathering purposes, like CAD, etc., password, who am I, try to see who the web server was running as, try to see if they could connect out to their own servers. And on top of that, 8% of attacks were used to gain control of the web server, so they try and set up a remote access program. And some of these were quite smart, as in they would remove the program from disk once it was running in memory. And in the real world, it's hard to get information about what organisations are affected by these vulnerabilities, so they don't usually publish it. But we know that a server used to run the elections in the state of Georgia in the US was compromised in December 2014, and this wasn't discovered until 2017. And that server was used to transfer electoral voters' registration files across the state. So, yeah, these effects are real. The next vulnerability we're going to quickly touch on is Heartbleed, which was a vulnerability in OpenSSL. OpenSSL can be found in pretty much on most products, things like Cisco products, F5 in Linux, AWS, Android smartphones, Wi-Fi routers, so it's very widely used. The vulnerability got its name from the heartbeat request of the TLS protocol that was used to keep connections alive, and it was this heartbeat that was exploited. So a client was able to send 64 kilobytes of data, and they would send a length attached to it. But what it turned out, OpenSSL wasn't checking the length that was being sent in, so an attacker could send 1 kilobyte of data, say it was 64 kilobytes, and get 63K of data back from the server's memory. And the attacker could run this again and again and again to keep getting more memory from the web server. So this improper input validation allowed attackers to read things like private key material, username and passwords, or anything in memory on the web server. Unfortunately, with so many products and companies relying on OpenSSL, you'd assume the product was well maintained and supported back in 2014. However, unfortunately, I had a single full-time developer working on it, 3 part-time developers. In terms of funding to the project, they were getting around $2,000 per year. I think it did get a bit more funding after this, obviously with the focus on it, but back then it did not. Gone one further, sorry. So with so few resources that I maintain in this project, code that was the Heartbleed exploit was accidentally included in February 2012 and it was released to the public, and it wasn't discovered until April 2014. The solution for Heartbleed, is the same with Shellshocked, was to apply an updated package to the system. However, with the Heartbleed, private key material could have already been stolen, so it resulted in a lot of websites and online services needing to roll passwords and private key material. A few notable organisations that were affected was Yahoo, who actually advised users not to log in for, I think it was about 6 hours, and to change their passwords after the patch had been done. And the Canadian Revenue Agency lost 900 social insurance numbers on a web server in a 6-hour window, and they had to end up shutting the site down. So the last exploit we're going to briefly touch on is Log4Shell. This was rated 10 for criticality as well. It was a vulnerability in the Log4j Java library. Let's try moving these up. It's better. If the application logged user input using Log4j, so if it was a web server and it was taking user provided input, you were able to exploit that web server. So an attacker could load and execute malicious Java code or orchestrate secret environment variables from the web server. This could easily be achieved by placing the malicious string within the HTTP request as like your web URL. And the Tenable CEO labelled Log4Shell as the single biggest, most critical vulnerability ever. It affected many vendors, both cloud and on-premise, and Ernst & Young estimated 93% of cloud environments were vulnerable, and after 10 days after the patch release, average orgs had only patched 45% of vulnerable systems. In terms of attacks that we know of, I believe Iranian government-sponsored actors compromised a US government department through an unpatched VMware Horizon server, and were able to move laterally through that department quite easily. But why was Log4Shell so much worse than the others? It was difficult to scan for Log4j. Because it runs within a Java application and it's not managed by system package management. So things like your standard sort of patching tools for Yum deb packages wouldn't be able to have visibility of it. Java libraries are maintained by the application vendor, so therefore they needed to publish a new version of the application for you to get the patched version of Log4j. So it makes identifying the vulnerable applications difficult, because not all Java applications were vulnerable, used Log4j, or may not have been configured in a way that it was vulnerable. You need to know which ones were vulnerable and the versions of that software to actually know. Fortunately, there was a workaround for this one. You could disable JNDI lookups or remove that class from the jar file. Next one. So luckily with Log4j, because it was hard to find, Google released an open source scanner, and it's compiled for Windows and Linux. and it was quite simple to use. You simply downloaded the executable, extracted it, and then ran it, and with a path argument of where you want to scan on the system, so you could limit it to program files or the whole root disk. It also came with an option to rewrite, so it could actually remove that vulnerable class file, so it was quite useful in that way. The unfortunate part was you had to SSH onto every single system, or RDP if you had Windows, to run it. And with thousands or tens of thousands of servers, that's a huge daunting task if you're not using any sort of automation. Even if you had 1,000 servers, 10 minutes per server, you'd be looking at multiple weeks with one tech working on it. And that's not even to remediate, that's just to identify them. So CVE patching costs organisations millions of dollars per year, and they still miss and leave systems unpatched for long periods of time. And that results in losses from old CVEs, which really shouldn't be hanging around anymore. So what is the solution? Obviously there's a better way to do this. So we want to automate the scanning. So we don't want to put our operation staff through this manual, repetitive, mind-numbing work. So we want to use automation where it makes sense. And just one thing, plagiarism is bad at school and university, but at work it's okay as long as you're not breaking copyright. So we don't want to start writing something from scratch. So let's have a look at what we've got here. So we've got the Google scanner, which is a binary that we can ship around and run. And in that case I work for Puppet Build Bolt, which is a free open source tool which allows you to automate tasks at scale across a wide range of servers. So let's just quickly touch on the two different types of Puppet. So Puppet's a configuration management tool for primarily Windows and Linux systems, and we have two types of Puppet. So decorative Puppet, where we specify the desired state of our system, and Puppet figures out how to achieve that. It's idempotent, so it won't continually keep running the same action again and again. So if you say install package X or write this file, it checks if the file or the package is installed and doesn't continually do it. And there's also on-demand Puppet, where we specify the exact steps for what we're doing. So we might say user add Ben, yum install this, chmod this file, etc. So Puppet can run with an agent or agentless. However, Bolt does not use agents and pushes configuration changes and updates via SSH and WinRM. So we're able to run this in an environment where we don't have an existing installation. You can use Bolt to automate simple tasks. You can use it to run a Python script or a Bash script or a PowerShell script. It doesn't really mind what you're going to run in. So I've developed a very simple Bolt plan which uses the Puppet language. As I mentioned earlier, you could have done this in any language. And yeah, I'll leave that QR code up for a second and then I'll jump on to the next slide. Oh, hang on, this is where I need to switch. And that didn't work. Sorry. Okay. So this is the Bolt plan that I was talking about. So it's not particularly long, 100 lines long, and we have some parameters at the top. So we take a list of targets. Is that font large enough, or should I make it larger? It's okay, because I can't really see it from here. Bigger, okay. That bigger? Yeah, we'll probably go there. Okay. So we take a list of targets. We have a couple of other parameters that we don't need to set, like where we want to install it. So C or /temp on Linux. So you can feel free to move it around if you have disk space requirements. And then we have a scan path. So obviously for Windows, scan C. But if you had other drives, you can change that. Linux, we just scan root, nice and easy. So we run the plan. So we collect the facts about our devices and our servers. So we get a list of a variable that has the Linux systems and a variable that has the Windows systems. So the facts is just information about it, like how many disks it's got, what's its IP address, and we're just checking the kernel version. And then for Linux, we simply extract the target.gz file, which is provided by Google on that GitHub repo I shared earlier. We extract it and we just make sure the scanner is mode 755, so it's executable. These are just checking the results to see if any servers failed. And then for Windows, even easier, we just have to extract to the zip file. There's no need to set log4j scanner to be executable because it's .exe. We then run the vulnerability scanner. So just running the command and then the scan path as required, and then across the targets that were successful. And same with Windows. We then get those results. We check to see which ones. So with the log4j scanner, if there's no output on standard out when you run it, it didn't find anything vulnerable. So if there's anything, we see any standard out that's greater than 1, we know it's a vulnerable system or it's found something at least. And I won't go through the bottom of this. We just present the results to the user. So let's see if I can get back to this PowerPoint. Okay. And we can skip those because we already went through that. So we have a demo as well, run it, so please work. Okay, that's working. So we've got 150 Linux servers here just running in AWS, and some of them are vulnerable to log4j. So we've got a Linux system here, we're running Bolt, which you can run on Windows as well. And on this one, and sorry I can't increase the font on this if it's too small, I've installed the scanner. It has instructions on the README how to do that. We can print out information about the plan so you can see the variables that we saw before. Bolt has an inventory file where we specify the servers that we want to connect to. So in here I've specified the 150 IP addresses for the Linux systems. We're just using SSH keys. So we run the plan, so Bolt plan run, name of the plan, and the targets being Ubuntu, which was the name of that group. I think it took about 5 minutes to run. I've chopped the video up so it's obviously way quicker, but we can see it stepping through the stages like checking the facts, checking the system, extracting the archive, and actually running the scanner. And once it completes, we'll get a result set of all the systems that were vulnerable or not vulnerable. I'm only reporting on vulnerable systems, so if it's not vulnerable, I just leave it out of the output. And there it comes back. So at the bottom, you can see there was 79 of those 150 systems were vulnerable. And then it's actually printed out the standard out that came from the scanner, so we can see which jar files were vulnerable. And usually by path, you could probably tell what application that was. There's also another demonstration, which is just running it on Windows, which is basically exactly the same. 40 Windows systems, if that's plain. Yeah, it is. 40 Windows systems. The only real difference with Windows is, I'm able to zip into this. We specify a longer connection timeout because for some reason Windows times out when I run this at 15-second timeout. So that should, yeah. So Windows obviously WinRM, username and password. No keys here, unfortunately. Oh, there we go. So the connection timeout specified for 45 seconds for the Windows systems. Others will get some timeouts. So run that and the results will be the same as the other one, just specifies the vulnerable systems. And yeah, it saves time. But I guess the point is, obviously this is an old exploit, and if you scan your systems now, hopefully this wouldn't find anything. But if there's anything new that comes out, or there's a way to scan or check it, use any sort of automation tooling or scripting to wrap it and run it at scale. So sort of the takeaways. Oh yeah, 22 hosts on that one, and then it also prints out the path where the vulnerable jar files were found. You could also run this with the rewrite flag that I mentioned earlier, so it would actually remove the vulnerable jar file. So you could also do that if you're confident that wouldn't cause any issues with your application. Okay, hang on. This does not want to go to the next slide. Yeah. Thank you.
Awesome. Big round of applause.